Hello everyone, in this video I will be presenting the design and a simulation of a multi-output power electronic converter, 3-phase 415 volt 50 Hz AC source. I am going to upload this Simulink model file in my website, and you can go through this video link or browse through the bio, and you can download the file and use in your projects or for your personal use. The main goal of this project is to generate multiple regulated DC output at a different voltage level and different power level from a single phase AC supply, while meeting industrial requirements such as voltage regulation, ripple limitation, overload tolerance, and electrical isolation. This entire system is analytically calculated and verified using MATLAB Simulink. The motivation first. The modern industrial system rarely operates with just one DC voltage level. In practice, you may need low voltage, high current supply for control circuit, medium voltage supplies for power electronics, and high voltage, low current output for specialized load. Designing separate power supplies for each requirement is inefficient and expensive. So the challenge here is, how do we generate multiple independent and well-regulated DC output from a single 3-phase AC source while keeping the system modular, efficient, and robust? That is exactly what this project addresses. So, firstly, the system architecture. The system begins with 3-phase 415 AC input, which fits our power supply or the converters. Firstly, we have 3-phase bridge rectifier. Then it converts the AC source, AC power to DC power, and then it fits different types of converters. I'm using buck converter for output 1 to output 2. I'm using isolated flyback converter for output 6, output 3, and output 4. And buck boost converter is used for output 5 and output 6. And finally, when we connect the buck converter and isolated flyback converter, I'm getting another output of output 1 to output 4 when they are connected in series. The key idea here is we have one DC link but multiple independent DC to DC converter, and this system architecture provides modularity, easy expansion. We can keep on adding here. So after converting the AC power to the DC power, then the rectifier converts and it provides the high voltage DC link, which acts as a central energy bus for the entire system. The measured DC link is, when I simulate it provides 537.7, and when I calculate it, theoretically it is coming around 556 volt. Okay, now next is the load assumption and load design philosophy. So all the load in these projects are assumed to be purely resistive. We do not know exactly what type of load we are connecting it. However, we are going to assume that it is purely resistive and simplify the analysis by eliminating the reactive power, phase shift, and load side energy storage. So we are going to use this simple basic power relation. Now at the output 1 to output 2, the converter should produce 25 volt DC. Then output 3 to output 4, it should provide 50 volt DC. And output, when these two converters are connected in series, they should provide 75 volt in a series connection. Therefore, the output 1 to output 2 will be able to fit the load of 166.67 watt. Output 3 and output 4 should be able to fit 333.3, and when they are connected in series, 500 watt load which can be connected. And output 5 to output 6 is a high voltage output where it will be able to produce 1000 volt or can be connected to the 1 kilowatt load. So total output power is 1500 watt or 1.5 kilowatt, and by assuming that the overall efficiency of the system is 90%, we require an input of 1.67 kilowatt. Now this is the Disylink calculations. For the Disylink calculation, why do we use this three-phase bridge rectifier? The three-phase bridge rectifier has 6 diodes, 2 or pair of diodes connected in series, and the three phase, each phase is connected to the middle of the each pair, and the output produced is our Disylink voltage. For stabilizing the Disylink voltage, I'm using a small resistor of 1 ohm, and we use this three-phase rectifier because compared to the single-phase rectification, it provides higher average DC voltage. It significantly lowers the ripple, and it is excellent. Provides the excellent robustness under overload condition. Now I have calculated where it can easily tolerate 200% momentary overload. Now moving into the details of a diode. The calculated peak inverse voltage is around 587, and considering the 20% input voltage spike, the peak inverse voltage comes approximately 704 volt. So by keeping that, the rectifier devices are selected with a sufficient safety margin. Now moving to the buck converter, and buck converter produces output 1 to output 2, which will produce at least 25 volt. Why do we choose the buck converter? It efficiently step down the voltage, maintain continuous current, and produce low output ripple in continuous conduction mode. So the key specification is we have a MOSFET or IGBT, then inductor, we have a capacitor, And PWM generator, we are providing a duty cycle of 0.045, and we are able to get the output voltage of approximately, yeah, we are getting 26.2. We require an output of 25 volt, and the current is 13.61. For detail inductor and capacitor values for or this PWM generator, you can just download and learn yourself. I'm going to uh, share this file too. Next is the isolated converter, 50 volt output. We require 50 volt output from the isolated flyback converter, for which is electrically isolated from the other converters. Initially, if you can do or you can use two buck converter to step down the high voltage of 537 volt to 50 volt, but when you connect this into a series, it is not electrically isolated. Therefore, you do not get the series connected voltage of 75 volt. Therefore, you have to use the isolated flyback converter, which uses a transformer. And if we use the two-buck converter approach, then it will fail due to a common ground path, and duty cycles will interact within each other. So flyback topology provides galvanic isolation. Then voltage scaling is easier while we use the turn ratio and save series connections of the output. So for this transformer ratio, 4:1 transformer ratio unit, transformer turn ratio is selected to switch this stress. And for flyback converter, the output of the primary secondary of the secondary of the transformer is connected to the diode and a capacitor. And primary, we have a line connected to the primary, and IGBT is connected to the primary side. And using the duty cycle and the PWM generator, it switches the input power provided, and we got the capacitor value of 0.6 e to the power minus 4. Then the duty cycle is 0.27, and when I simulate, I'm getting 48.34. However, there is a small voltage drop. We require 50 volt. This voltage drop is because of the internal transformer losses. Now, when I connect them together, I'm getting 74.54 volt, where I require 75 volt. And all the loads are connected here. Load 1 is 3.75, which we calculated 3.75 here, and similarly other loads are provided. Okay, now finally the buck boost converter. The output 5 and output 5 to output 6 O5 to O6 or output 3 should be variable voltage output. The most demanding output, it should provide 0 to 1000 volt DC adjustable output. This requires step down and step up capabilities. So therefore, we have to use a buck boost converter, as it can regulate voltage above or below the DC link level. The duty cycle is 0.65. Maximum duty cycle is 0.65 and minimum is 0.1. This slider, by changing this slider, we're able to get, when I use the duty cycle of 0.65. Firstly, I will show you the buck boost converter here. Each buck boost converter has IGBT, then inductor, diode connected in this topology, and a capacitor here. So I'm using a repeating sequence and operational relational operation to compare the duty cycle and the repeating sequence waveform or triangular waveform, and it will produce the pulse. This pulse is provided into the gate of our IGBT, and it controls the switching of the IGBT. Finally, controlling the voltage from at the output. At the duty cycle, when we use a duty cycle of 0.64 volt, I'm able to get 1024 volt. If I reduce this duty cycle to 0.3, I am getting 320.3 volt. Now if I further reduce, I'm getting 0.2 volt. At the duty cycle of 0.2, I'm getting 210. At 0, I'm getting 1. Yep. Now I have a simulation here. The scopes for the buck converter. This is an input 3-phase voltage RYP waveform in a sinusoidal waveform, and my output DC current is ramping up and is providing around 25 volt here. And this is output current, sorry. This is an output voltage. Now we have a diode voltage and inductor voltage like that. Similarly, for the flyback converter, we have input voltage, output current, and output voltage with reasonable ripple limits. Now, looking at this simulation results, we confirm that the voltage regulations are within plus or minus 5%, and the ripple is below the specified limit. Then we have a stable resistive loading. In conclusion, we can now say that the project provides a robust, modular, and scalable multi-output for electronic converters. You can add other converters if you require the below the buck boost converter. and uh, you have a series for the series connection of a buck and the flyback converter. You are getting 74.5. You have an input power of 9 and the source line to line voltage of 115 volt. That's all for today. Thank you. Uh, Thank you for watching. If you found it useful, feel free to like, share, and ask questions in the comment box. Please go through the link given in the description so that you can download this Simulink file and all the calculations that I'm going to upload. Thank you.